Antarctica and Greenland and their implication in terms of sea level rise and the different challenges these two regions faces. So we're going to start with Jason Box, which is a glaciologist at the Geological Survey of Greenland and Denmark, and is going to talk about Greenland ice sheets and its different implication in terms of sea level rise in the future. Welcome, Jason.
Thanks very much for being here. I'll be giving a kind of a sneak preview for the slides I'll present at 6 p.m. today. And the purpose of this session, I understand, is to compare Greenland and Antarctica. I will emphasize the elevation. Closer to the mic. Louder. Okay. So I'll be talking about the so-called melt elevation feedback from Greenland. And as you can see from the title here, it's Greenland moving beyond its threshold of viability. Just wanting the slide to advance. Is it off? Okay. Okay, so cartoon of the melt elevation feedback for Greenland. Surface melting causes thinning, and the atmosphere is warmer lower down. And what that does is it enforces more melting because the atmosphere is warmer lower. So on the right, the lowered surface into warmer part of the atmosphere. The parabolic shape of the ice means that it's a nonlinear increase in the area of melting as the surface draws down. Most of the impact is in the first few degrees of warming. This is the loss of 10%. It's the same shape for any volume of Greenland. The amount of time it takes to lose a fraction of Greenland ice increases most strongly in the beginning as temperatures increase above some stable threshold. And the reason it has this shape is the recent climate for Greenland has been stable until about 1980, as recently as 1980. And the projected warming that I'll show you drives Greenland beyond that state of stability. As Levermann and Winkelmann put it, I'll show you two different visualizations for so-called hysteresis, and that's another way of talking about irreversibility. Warming in the upper part of this graph, it says the current state of the ice. You can warm and cool back and forth, and the ice mass remains stable because you haven't yet tipped over the threshold of viability. However, if there's enough time spent beyond that threshold, the system can end up in the lower part of the ice where temperature fluctuations, warm and cold, don't push it back into a stable phase. Graphics a little hard to understand quickly, so I've got another version of this that I think is helpful. And so you have temperature anomaly. That's temperature above some stable thresholds on the lower horizontal axis, and then the volume. So the story here begins in the upper left of this curve. And if the symbols work right, yes, temperature can fluctuate back up and down. So it's like the roadrunner running off the cliff and running backward before it realizes that it can fall. So we can have a really short melt event that does a lot of damage, but if the climate can return to a cooler phase, then we stay in a stable regime, kind of like you saw in the previous graphic. So there we are, fluctuating up and down in temperature with the weather of the system. As that temperature anomaly exceeds, in this case, the best estimate for Greenland's threshold of viability is 1.6 Celsius above pre-industrial. And if we spend time there, it's like the roadrunner and the coyote are off the cliff and they look down. And then the system then collapses. Volume is dropped. You can see by a factor of 4-ish. These are results after Alex Robinson and others' work demonstrating this so-called hysteresis, this irreversibility. What is the threshold for Greenland's melting? And the next slide, I used a wider and a longer arrow because it takes much more time to build up the ice than it does to melt it. We see that we observe that in the field, and even the sea level curves from the past 800,000 years also show that sea level rise coming out of the ice ages is abrupt, and sea level drawdown going into the next ice ages takes a lot of time. And so the system can stay, will stay in this low volume state until another ice age occurs and regrow the ice. That takes longer again. So here are Greenland temperatures on the red curve since from 1840 to 2022. There has been 1.2 Celsius of summer Greenland warming above the past century. I'm using that as the baseline here. And on top of that, I put the CMIP 6 summer temperature projections for Greenland only. And the fossil fuel intensive or high emission scenario is the upper curve, and a Paris-like curve is the blue curve. And so you can see that the future projected warming is around 5 Celsius by end of century. And we could talk about the deviation between the models and the observations there in the first decades, but I think it's not that important. I think what I want to point to here is it's about 5 Celsius by end of century for Greenland. And according to Levermann and Winkelmann, they estimate that it would take 500 years for 10% of Greenland ice to be lost at this warming rate of 5 degrees. 500 years for 10%, that's 70 centimeters of sea level rise. However, the modeling system they used to develop their estimates arguably isn't moving ice as quickly as we observe. So the timing is probably less than 500 years. And so the best estimate from Robinson and others' work was a 1.6 degree viability threshold for Greenland. But as you can see from the curve on the right, it's actually a probability distribution. It could be more, it could be less. The 1.6 is just the median of that distribution. And given the projected warming, nevertheless, it's inevitable that Greenland crosses its viability threshold. And right now we're at what, let's call it 1.2. There's still some warming that Greenland can tolerate before it comes into a state of irreversibility. And I emphasize that the results are based on a simple approach, which, according to observations from the field, the ice can move faster than this. So I think the level of certainty that we have is low. What we do observe here is surface elevation change or thinning from Greenland, and in a number of areas there's 300 meters of thinning from 2000 to 2020, and the main thinning is at tidewater glaciers, and this thinning into warmer parts of the atmosphere corresponds with an additional air temperature increase of 2.5 Celsius, up to 2.5 at the 370 meters of thinning. So we can conclude that the elevation feedback is started because there already is impressive thinning. You can see for the box covering West Greenland, there's an average thinning of 170 meters. There is observed thinning on the Northeast Greenland ice stream, and the thinning and the associated warming is near the so-called equilibrium line altitude. So that means that the snow line elevation will be pushing up and exposing a wider area to darkening process. That's an amplifying feedback. So this is only the elevation feedback, but there are other related feedbacks that can deliver the ice faster. Greenland is mainly a surface melt dominated ice sheet. As a colleague put it, the mass balance game is played at the surface. And I think there are parts of Antarctica, especially the peninsula, where seasonal melting is strong, but not just the peninsula, other areas that Chris will talk about. The Antarctic was named precisely because it's quite different from the Arctic, with a continent centered at the pole, whereas the Arctic has an ocean centered at the pole. Greenland is more an obstruction to atmospheric circulation, so it's very sensitive to that. It'll be interesting to hear Chris Stokes talking about how different Antarctica is. I think that's the only slides I put together quickly for this session. Thanks for your attention.
Great. You're taller than me. Thank you, Jason, for this talk. And I think you introduced quite well Christopher Stokes, that is going to present you a different threshold on the Antarctic and Antarctic Peninsula. So Chris Stokes is a glaciologist from University of Durham. And after his presentation, you can ask questions to both Jason and Chris.
Thank you very much. Yeah, so I'm going to try and build on what Jason said there about Greenland and draw out some similarities and also some differences between the two ice sheets. And I've showed this slide before at COP And I think it's a really important one because we're so focused at the moment on making observations over quite short timescales when it comes to ice sheets, or looking at plots of modeled ice sheet outputs. And actually, if we just look back in the paleo record and we look at this example here from North America, this was the big ice sheet. It was as big as Antarctica, and it grew and then it decayed relatively rapidly. And it's a really good example of how ice sheets can contribute to sea level relatively rapidly, because during the last ice age, about 20,000 years ago, when we grew ice sheets over North America and in Europe, but also Antarctica and Greenland expanded as well, we know that sea level was about 120 meters lower. And you can see that on the right-hand plot there, which is taking you from thousands of years ago to present. And you can see on the plot there that when these ice sheets deglaciated, from a period of about 20,000 to say 12, 11, 10,000 years ago, all of that water was put back into the oceans and sea levels increased by about 120 meters, but it wasn't linear and steady. There were times when sea level jumped quite rapidly. I've labeled one on the plot there, Meltwater Pulse 1A, when we think, albeit with uncertainties, that sea level could have risen by 4 meters per century. So that's 10 times faster than current rates. So we have some lessons from the past that tell us that ice sheets can actually put water into the oceans very quickly, and on timescales that will be very, very difficult to adapt to. So I says at the moment, sea level rise is just under 4 millimeters per year. We know that the contribution is largely from Greenland, as Jason's just alluded to, but also from West Antarctica. And we know that that's accelerated. So the IPCC explained that that has accelerated about 4 times over the last few decades. And as Jason said, in Greenland, this is forced largely by atmospheric temperatures. So warming of the atmosphere creates higher surface melting. But also elsewhere, particularly in Antarctica, but also in Greenland to an extent, we know that warmer oceans are leading to mass loss and contributing to sea level rise. And that process is far more important in Antarctica than Greenland. So this assessment here is showing you what, I guess, a summary of some of the things that Jason touched on there. This is the sea level rise from the Greenland ice sheet over the last few decades. It's added about 11 millimeters to global mean sea level. And about half of that was contributed to from melting of the surface, and about half was related to dynamic processes. So sometimes that's melting from the surface, impacting on ice flow dynamics, or it could be from ocean warming, allowing melting of tongues and speed up at the margins, which carves more icebergs and leads to sea level increase. So these processes are not mutually exclusive. They can work together in some cases as well. But the key point is that surface melting is very important in Greenland compared to Antarctica. If we look at Antarctic losses then, and Antarctic contributions to sea level, we get very little surface melting. In fact, surface melting in Antarctica in terms of mass loss is pretty much negligible. All of the mass loss from Antarctica is from warming oceans that are thinning the floating portions of the ice sheet. That's like weakening the buttressing, this weakening a doorstop of floating ice in front of these glaciers. And when you do that, you increase ice discharge from inland, and that can contribute to sea level rise. And you can see from the plot here, the overall contribution from Antarctica is less than from Greenland. So it's contributed about 9 millimeters to, sorry, about 7 to 8 millimeters to global sea level rise over the last few decades. And nearly all of that is from West Antarctica, which is the green line. The Antarctic Peninsula has smaller ice caps and glaciers, and that they are melting, and they are contributing to sea level rise. That's the little branch of Antarctica that sticks up towards South America. But the East Antarctic ice sheet, which is by far the largest part of Antarctica, is at the moment in equilibrium, possibly even gaining mass slightly. I find that interesting because East Antarctica is by far the largest ice sheet. We had a session earlier today. You'll be able to, I guess, go and look at the recordings of those where we focused almost entirely on East Antarctica because it's by far the largest ice sheet on the planet. It stores about over 50 meters of sea level equivalent. It's an order of magnitude larger than West Antarctica, but there are order of magnitude fewer publications on that ice sheet. But I think that's starting to change. And I think we're also starting to get a little worried about what's happening in East Antarctica now, which is why we had the session earlier today. This map here It's quite similar to the map that Jason showed of Greenland. It's showing you kind of ice surface elevation changes. They've been corrected slightly to give you a kind of volume losses in meter of ice per year. And these red colors are mostly found in West Antarctica, where we're seeing very high rates of mass loss due to that dynamic discharge of ice. But you'll notice as well that there are parts of East Antarctica that are also losing mass, where you're seeing the red spots over in places like Wilkes Land. This is an area we've been keeping an eye on now for a couple of decades. And there seems to be, this is not just variability, there seems to be a trend emerging of mass loss also in East Antarctica. And this part of East Antarctica shares characteristics with West Antarctica. This is part of the ice sheet that is grounded on the seabed, and the land slopes inwards. So if you start retreating the ice sheet, you're taking it into deeper and deeper water, and that's a very unstable situation for an ice sheet to be in. And you can see that most of West Antarctica is grounded well below sea level. They're the blue colors. But also in East Antarctica, there are a couple of other basins that I've labeled there. The Wilkes subglacial basin, and also the Recovery subglacial basin. These are deep subglacial basins where the ice sheet is retreating back into deeper and deeper water. So if you like, we've got 3 mini West Antarctic ice sheets within the East Antarctic ice sheet that we need to keep an eye on. Why do we need to keep an eye on them? Because these marine-based sectors are potentially vulnerable to 2 important instabilities. The first of those is the marine ice sheet instability, which you can see in the top cartoon there. And we've known about this since the 1970s when it was first proposed that this situation in an ice sheet could lead to quite high rates of mass loss. Because what happens is that once you push the ice sheet grounding line, that junction or that place where the ice begins to float, if you push that back into deeper and deeper water, it's a self-sustaining positive feedback because you can't balance the mass required to keep it stable. So it'll keep increasing in discharge until it finds some ground that's higher elevation, which it can then pin itself to in shallower water. So as I said, we've known about this for a long time. It's theoretically robust. We've seen observations of it where glaciers have retreated across over-deepened beds and they've accelerated. And it's got high potential in West Antarctica. In fact, there are papers out there where some scientists have proposed that the marine ice sheet instability is already underway. It's already been triggered in West Antarctica. It's potentially irreversible, which is worrying. Not everybody agrees, of course. But there's also high potential for this to take place in those 3 subglacial basins in East Antarctica as well. The other cartoon on the right shows you something called marine ice cliff instability. And you don't necessarily need the bed of the ice sheet to deepen inland. But this is where if you can very quickly remove the floating ice shelf in front of the ice sheet, then you have essentially, you expose a very high ice cliff in deep water, which becomes unstable and collapses into the ocean. And then because your ice sheet gets thicker inland, that's also a self-sustaining feedback. And so we're particularly worried about this process. It's only been kind of theorized about relatively recently. There are some limited observations that would support it. But I think this process could potentially be quite important in East Antarctica, perhaps more so than in West Antarctica, actually. So we're particularly worried about these 2 instabilities, which could lead to quite high rates of sea level rise. The other thing that we're starting to get worried about in Antarctica, and again, this is much more so in East Antarctica than West Antarctica, is that there's quite high rates of surface meltwater now being detected on the surface of the ice sheet. So if you like, we're seeing a situation where many of the floating ice shelves are being covered in meltwater ponds. Those meltwater ponds, in some cases, might mean that they can drain into the ice and they can fracture it apart. And we've observed that in the Antarctic Peninsula in 1 or 2 places. We haven't yet observed it elsewhere in Antarctica in the west or the east. But I think East Antarctica in particular is going to be vulnerable to this because the East Antarctica actually extends quite far north into quite low latitudes, further north than the Antarctic Circle. So there are likely to be some very vulnerable ice shelves in East Antarctica in the future. How close are we to thresholds of instability, I think, is a really interesting question to ask. What kind of emission scenario would mean that we start to fracture apart and collapse some of the ice shelves around East Antarctica? Well, this is a map that's comparing melt rates on the Greenland ice sheet at present. And then on the right is a map of melt rates over Antarctica at 2100. So that's under a high emission scenario. So what we're saying here is that it might only be another 100 years or so until we start to take parts of Antarctica to melt rates that are as high as present-day Greenland. And we've just heard Jason articulate quite how worrying some of those melt rates are. And some of the red colors are clustered around the Antarctic Peninsula, but also around West Antarctica, and also around some quite small ice shelves in East Antarctica that we know at the moment are holding back some of the ice further inland. This is some more predictions of what might happen in Antarctica. The top row there is showing you the meltwater runoff, and then the surface mass balance, the balance between the mass input and the mass output. And then it's showing you on the top row is 1.5 degrees of warming, the second row is 2 degrees of warming, and the third degree is 4 degrees of warming. And again, you can see that both melting is going to increase, which will make some ice shelves potentially vulnerable, but also there will be some precipitation increases in Antarctica, which will be an important part of the mass balance. But a lot of the modeling shows that the increased melt rates will be far greater than any compensating increase in terms of precipitation. And this is a bit of a complicated plot here, but it's showing you a number of ice shelves in Antarctica at present, and it's showing you some of the thresholds that you might cross in the future. So this line here is showing you the collapse that was associated, or the melt rates that were associated when we obliterated the Larsen A and the Larsen B ice shelves. And then the blue bars are showing you under a low emission scenario, or mid to low emission scenario, that some ice shelves, such as the Larsen C, the first one on the plot there, on the left-hand side, will start to exceed that threshold. But under a high emission scenario, we start to take Larsen C with the Wilkins ice shelf, George V, and several other ice shelves around the Antarctic Peninsula. But also some of the other ice shelves in East Antarctica, the West and the Shackleton, under high emissions, start to approach some of those melt rates that we know fractured apart some ice shelves in the Antarctic Peninsula. I think something that was touched on earlier today as well was that we sometimes look into the deep past to see what happened to these ice sheets during past warm periods. And it's quite worrying, certainly for Antarctica. We know, for example, during the mid-Pliocene, about 3.5 million years ago, temperatures were only 2 to 4 degrees warmer. Sea level was 10 to 25 meters higher. So we know that if we sustain But then the dashed line there is showing you, again, it's what we call or refer to as low likelihood, but very high impact. And current understanding is not yet able to rule that out, that dashed line that takes you to very high sea level. And of course, you have to even change the figure to go out to 2300, that vertical bar on the right-hand side there, showing you under a high emission scenario, 5, 6, 7 plus meters of sea level rise. Up to 15 meters can't be ruled out according to some of the numerical model simulations that build in some of those instabilities. And then just to finish, there was a recent synthesis of global thresholds related to climate change that we might pass if we exceed 1.5 degrees of warming. And this includes things on here, you might not be able to read it, but it's got coral reefs, it's got the boreal permafrost, lots of different elements of the Earth system. But ice sheets are in here as well. And what you can really clearly see is, as Jason said, Greenland we may have already crossed the threshold for Greenland. I think Jason's going to be talking later on today about the fact that if we were to assume that the warming that's taken place in the last 10 years is going to continue, then Greenland may already be on its way in terms of that melt elevation feedback. West Antarctica is also very close to passing its threshold, and there are studies out there suggesting that we may have already passed the threshold with ocean warming that's leading to irreversible retreat. So you can see there their estimates of the thresholds. Greenland 1.5, possibly as low as 0.8 or as high as 3 degrees. But I think the evidence is fairly persuasive now that something seriously is happening in Greenland. West Antarctica not too far apart, central estimate of 1.5, could be as low as 1 degree, could be as high as 3. And then for the first time, East Antarctica's marine basins has been added as a new kind of global tipping point that we need to be aware of, with a central estimate of 3, but could be as low as 2, could be as high as 6. And even the whole of East Antarctica now is being added to this kind of hot list of things to watch in the Earth system. But obviously you need a much higher threshold to get rid of some of those terrestrially based ice in East Antarctica. So I shall finish there. Thank you very much.
Yeah, thanks. Great slides. East Antarctica is very intriguing because, as you say, a factor of 10 fewer studies, and it's coming into focus now. The driving stress, given the shorter distance from the ice shelf to the very thick parts of the Antarctic ice sheet, you're getting up above 3-4 kilometers within a shorter distance than on the West Antarctic ice sheet, if I'm not mistaken. Wanted to get your reactions about the driving stress question, and then the modeling that has been done. I think it's on a flow line, a central flow line, and when you have a case like the East Antarctic case, when there's kind of more of an amphitheater shape of that drainage basin. And I think as we've seen in West Greenland, its fastest glacier, the biggest one, there's perhaps a damping feedback from the ice kind of avalanching in from the sides. Is that in the considerations for the East Antarctic sectors?
Yeah. So it's really good questions there, Jason. Thank you. And yeah, I think you're exactly right. I think in East Antarctica, we've got some quite small ice shelves that are providing quite a lot of back force, what we call a buttressing effect. They're like doorstops holding back the inland ice. And in some of the model simulations, some of those ice shelves will disappear. And because you've got such a thick ice sheet behind, I think the mass throughput we would expect to be quicker because you've got steeper slopes, higher driving stresses. So the velocity increase that you'll see in those situations will be very high. The one thing that might help is that some of the glaciers are still in quite deep and narrow troughs. And so the lateral stresses become important there and could hold back some of the ice. So those kind of stresses kind of take me on to your second question, which is, can the modeling in some ways, is it able to represent some of these really important processes? So I think the modeling that I showed there was from some of Rob DeConto's work, and this is the kind of the whole ice sheet model. So in that sense, the different sectors, the different catchments are allowed to speak to each other, and I think you will see some effects. We know, I mean, I've done some work on the North American ice sheet, which disappeared at the end of the last ice age, and when you see one sector rapidly draw down, it does tend to have a kind of dampening effect elsewhere, because you all of a sudden start to change the surface slopes, change the position of ice divides, and also change the way that subglacial meltwater is rooted at the bed, which in some cases means that you sustain it in one sector, but you starve meltwater at the bed of other sectors and dampens them down. So the models do have those processes in, whether they are fully able to represent them at the scale that's needed, because necessarily the model cells are quite large. Well, that's another question. And but yeah, I think there's going to be some interesting. The models are going to have to improve to be able to represent some of these processes that you've alluded to. Any other questions from the audience? Yeah.
Thanks. I'm confused by temperatures. So a lot of the temperatures you're talking about are the global mean surface temperature. But we're told Antarctic is warming 4 times faster than the global mean. And obviously, Greenland's in the Arctic, so it's feeling the higher temperatures. So can you sort of clarify that? And also what's happening in Antarctica? Because I guess it's not warming as fast because it's not losing sea ice.
Yeah, no, that's a really good question. And Jason might want to come in on this. So you're right, just to clarify that a lot of the temperatures that we're talking about here are global mean temperatures. We know the Arctic temperatures are amplified. They may be, we think now, up to 4 times higher over the last few decades than the increase we've seen elsewhere. In these situations here, when we're talking about temperature of +1 or +2, we're not talking necessarily about the temperature in Antarctica, what it will be like in 2100. We're talking about what we force the models with. Yeah. So we do have climate projections for Antarctica. So we have a whole series of climate models that will give you, if you want, what the temperature in Antarctica is projected to be in 2100, 2200, 2300. And so that's what we force the models with. We don't necessarily assume that that will be what the temperature will be in Antarctica. It could be higher, it could be a bit lower. But actually in Antarctica, my understanding is that the global mean temperature is not too far off from Antarctica. There are parts that are warming very rapidly, like the Antarctic Peninsula, but the rest of Antarctica is probably much more in line with the global mean temperature. Whereas in the Arctic, we're seeing huge temperature increases that are way above. So I don't know, Jason, if you want to come in on that.
Got maybe some good news that what I'll present later is Greenland is warming under 2 times the global rate, whereas the Arctic Ocean, that's 4x. So Greenland has an atmospheric circulation that is actually protecting it, and it's part of the reason why there's still an ice sheet there and not one over Canada, North America. And just a note about the mid-Pliocene, 3-ish million years ago, Greenland ice was almost completely gone.
Yeah.
So the onset of Greenland ice is thought to be around 2.5 million years ago.
Just to add to the question on temperature, I might have missed it. I'm sorry, I came in a bit late. But what about the impact of the ocean temperatures? I thought that was one of the key risks on the West Antarctic ice sheet, was actually the warming from below. And what do we know? What are the models telling us about the trajectory of that change?
Yeah. So that's a great question. You're completely right. So in Antarctica, what you'll do is you might prescribe a warming of, say, +1 degree at 2100. And then you'll have something in your model that will feed that into the ocean temperatures, which then you have to tell the ice sheet in your model react to these ocean temperatures. And so we know that in Antarctica, it's going to be the ocean warming that will do most of the damage, at least in the short term. I think going out to 2200, 2300, I showed some of those melt projections. that's when essentially parts of East Antarctica might resemble what Greenland looks like now. But in the next century or so, it will be the ocean temperatures that will do most of the damage. And we know, for example, in West Antarctica, we're getting this warm circumpolar deep water creeping up from depth, coming onto the shelf. It's melting the floating portions, and it's weakening that buttressing effect. Surprisingly, there are very few records of long-term ocean temperature change in Antarctica, or maybe it's not surprising, it's very hard to measure them, but we have very few long-term records of ocean temperature change in Antarctica. So we're reliant on models. We're reliant on taking a model, saying if atmospheric circulation changes, if the westerly winds change, if they weaken, if they shift position, what does that do to the pumping of warm water, that intrusion of warm water onto the shelf? And people are looking into this, and there's a recent paper suggesting that there will be a lot more warm water around East Antarctica in the next century or so. So on those timescales, that is very worrying, and we need to keep monitoring some of these big glaciers, because there is some recent work suggesting that under current climate change, we will see more warm water get into these glaciers and melting them. And we've done some experiments, very simplified experiments, where we assume that relatively cold waters around East Antarctica are replaced with relatively warm waters. And there's a huge impact on mass loss if there's a kind of regime shift from dense shelf cold water to warm circumpolar deep water. So,
yes, I'd like to add on that. The majority of mass or ice melt ablation from Antarctica is underwater, not from iceberg calving. And a feedback of concern for the future is, as surface melting increases and presumably the accelerated glacier flow from loss of buttressing and retreat into the reverse bed slope will put more fresh water near the surface. And that caps radiative cooling of the open ocean and can lead to an accumulation of heat underwater that would otherwise have radiated due to the freshening of the surface.
did you want to come in?
Hello. Hi, thank you very much for the presentation. I was just wondering, do the models consider the feedback mechanism of the release of greenhouse gases, ocean, carbon, methane, etc., or are they analyzed, or do they work in isolation? How does that feedback loop of the release of greenhouse gases work on your estimates and scenarios?
Yeah. So when we're modeling ice sheets in Antarctica, are you referring to like the feedback with melting permafrost? Yeah. Okay. Yeah. So I guess in Antarctica, there's actually not that much permafrost. The ice sheet is very thick, and it's warm at the bed effectively. In Greenland, I mean, Jason might be able to come on to this. In Greenland, I'm not sure what the extent is of permafrost around the margins of Greenland, but elsewhere, most of the permafrost on the surface of the Earth is actually not in glaciated regions. So it's there at the moment, and of course the climate models that are used will assume that as you increase temperatures, you will start to melt some of that permafrost. That will be an additional source. So these are what we call like the full kind of Earth systems models will include all of these feedbacks, and all of those feedbacks then are fed into other models that ice sheet modelers will use to force their models with temperature, etc. So yeah, they are built into the Earth systems models. Yeah. Yeah, they will do. Yeah.
Thank you for your presentation. You showed this IPCC figure with low probability, high impact, and that is based on actually the highest scenario. Are there also estimates for the lowest two scenarios? Because the process might also occur for a lower emission scenario.
So You mean could some of those instabilities take place at lower emission scenarios?
Yes, that's what I mean.
I guess they could do. Yeah. I mean, I think what you're seeing with that dashed line is all of the worst case scenarios happening quickly and at the same time. But yeah, absolutely. You know, some of those blue lines at the bottom there, the same models will have those instabilities allowed to happen, but they just don't happen when you've got lower temperatures and your oceans are cooler and your atmosphere is cooler. You're less likely to see those instabilities happening at the lower emission scenarios. In fact, they don't happen. Yep. So it's when you allow those instabilities and you have the high forcings that they tend to, you get these very, very scary worst case scenarios. Yep.
So just to add up on Chris, actually they do happen, the instability in the low emission scenarios, they just happen after, on a longer time scale. Yeah, but they do happen because low emission scenario is already 1.5 degrees, and in the past with the same warning, they do happen. So in the simulation, they also happen, just takes a few more centuries in the future.
But if you look at the lowest scenario, which is the Paris scenario, so the temperature should stay somewhat about 1.5 degrees also after 2100. So what happens then?
Well, this is because we do not say, I mean, so the low emission scenario does not prevent instability from happening. It's just limiting the magnitude of sea level rise that derives from the instabilities. That's a bit different. So it's a way of saying if we stay below 1.5 degrees of global warming, sea level rise will happen, but it will be limited to 2 to 3 meters by 2300. It doesn't mean that the high sheet just stops retreating afterward. It's just retreating less and less fast. But let's say it buys us sometimes for adaptations. That's the concept behind. Unfortunately, let's say.
And I guess that's a good point, that it partly depends on the ice sheet as well, because I think what we've seen here is that Greenland is very, very vulnerable. You know, so we're already committed to sea level rise from Greenland over centuries, and then West Antarctica is also very vulnerable, and then East Antarctica at the moment is the least vulnerable, and maybe a 1.5 scenario might actually protect most of East Antarctica. We don't know, but if there's one ice sheet that we can protect, that would be the one that we should be looking to.
So I'll try another question here. In the spirit of solutions that, or hedges, temporary interventions that slow down some of these losses, that buy us time while we eventually get our carbon budget in order, presuming we do. If we don't, none of it will matter. Have you modeled any of those sorts of interventions, from things that are more benign to things that are less benign?
Yeah, I think actually, I don't have the slides to hand, but I know, for example, in the De Conto et al. Paper that I showed some of the pictures from, the slides from, they do have some scenarios that are kind of buried away in the supplement of that paper, where I think they take carbon out of the atmosphere. They have some mitigation scenarios, and they show that that there are some dangers with overshooting, that you start to pass some of these thresholds, and then the hysteresis that Jason talked about takes over, and it's a lot harder to go back to where you were. We could pass a threshold in 50 years that could take 1,000, 2,000 years of cooling to go back to. That's the problem with ice sheets, I think. But it's not often being done in the modeling community. I don't think. I've seen some examples where carbon's removed and they lower, but
so just to be clear, carbon removal would be one of those, but slower. I'm talking about more rapid types of intervention like SRM, marine cloud brightening. In the Arctic, there's been talk about reflective silica beads on ice to slow the loss, et cetera, et cetera. Have people modeled any of those?
Well, there's a study led by John Moore and others, where the idea is to put up a sand or gravel berms to block the warm currents. And the latest iteration I've heard is a kind of a curtain, presumably on a Gore-Tex or a fabric that could actually keep these warm currents from impinging on the underbellies of the ice, and hopefully letting wildlife come and go. And they've costed those, and then they compare the cost of that big project to the cost of coastal flooding, and it's a lot cheaper on paper to do an intervention now to try to block warm currents than to re-engineer your coastlines globally. And then they actually argue not, deposit the money now. They say, therefore, we should study this and maybe use a small tidewater glacier in Greenland as an analog of Antarctica at a paltry cost of a few $1 million or so.
Yeah, I guess my problem with this kind of direct intervention is that if you're still heating the atmosphere and there's still carbon dioxide, the heat has to go somewhere. Yeah. So eventually what you end up doing is just pushing the problem somewhere else. We might be able to block water going onto one glacier, and it's just going to end up, the heat is being produced because of the greenhouse gases. They're in the atmosphere, and we're just pushing the problem somewhere else, probably. So my understanding is that the viability of these, the scale at which you would need to intervene to protect the whole ice sheet, it just would not work.
Great. Thanks, Chris and Jason, and thanks the audience for that many questions. I think we have a break now, and then we'll have a follow-up with Jason Box and other about Greenland ice sheets. So we can continue this discussion later.